So I'm going to talk about something called log-concave polynomials, matroids, and some applications to graph expansion. So this is joint work with Nima Anari, who's in the back, and we'll give sort of the follow-up talk right after mine, Kwikwi Liu and Cheyenne Oves-Garan. So first off, I just wanted to define some terms. So in particular, I want to start off with matroids. I'm sure many people in the audience are familiar, but just to make sure. So a matroid is going to come with a ground set, which for me is just going to be the numbers 1 through n. And I'm going to define it using its independent sets, which is a collection of subsets of the ground set 1 through n satisfying some properties. It should be non-empty. It should be closed under taking subsets. So if I have some subset in my collection, then any subset of it is in my collection. And then it should have this sort of exchange property where if I have two subsets of 1 through n in my independence that I am calling independent, and one is bigger, then I can take some element from the bigger one and add it to the smaller one, and again get an independent set. Those are the rules. And just to throw some more terminology at you, so the bases are also going to be a collection of subsets of 1 through n, and they're just going to be the independent sets that are maximal under inclusion. And this third bullet point will show that actually any of the subsets, any of the bases will have the same size, and that size is going to be called the rank of the matroid. So matroids are combinatorial gadgets that are trying to extract sort of the combinatorics of independence from various examples. And one of the motivating examples and where all the language comes from are linear matroids, which I get from taking, say n vectors over a vector space, in a vector space over your favorite field. And if I do this, I can get a matroid by taking the collection of vectors, or the collection of indices of vectors that correspond to linearly independent subsets in this vector space. And if I look for a maximal linearly independent subset, then I get a basis for this space in the linear algebra sense. And you can check that, being linearly independent, a subset of vectors being linearly independent satisfies all of these things. If I have a collection of vectors and they're linearly independent, I can remove them and I'll still get a linearly independent set. If I have two collections of linearly independent vectors and one is bigger, then I can take one from the bigger one and add it to the smaller one and get something linearly independent. And so just for a concrete example, if I pick these 4 vectors in R2, really R2 of the screen, so the singletons are all independent, and also any pair of them is independent and forms a basis for the space. So in this case, my set of bases is just all collections of 2 elements from the numbers 1 through 4. 1, 2, 1, 3, etc. Another one of the canonical examples are matroids coming from graphs. So suppose I take a connected graph with n edges. And so now subsets of 1 through n I can think of as subsets of the edges of this graph. And in this case, I can get a matroid by taking independent sets to be acyclic subgraphs. Subsets of edges that don't have a cycle in them. And if I take a maximal acyclic subgraph of a connected graph, what I end up with is a spanning tree of the graph. You can check this again is actually a matroid. And just for example, here I have a tiny graph with 5 edges, and I can just record what subsets of edges give me a spanning tree of this graph. So like 1, 2, 3 is a spanning tree of this graph. 1, 2, 5 can try and find them all. But that's my set of bases, and then any subsets of those are. So a set is independent if it's a subset of some basis. Those are the rules. So one of the themes of the talk will be working with general matroids, but a lot of the benefit of doing this is it covers sort of lots of cases that you're interested in sort of with one combinatorial structure. In particular, something I want to do is assign probabilities or weights to the bases of a matroid, and think of maybe sampling a random basis of some fixed matroid. And one way I'm going to record this is by using polynomials. So if I have some polynomial with non-negative coefficients, and let's say that it's the only monomials show up are products of disjoint variables, I'm going to associate to that a probability distribution on the subsets of 1 through n, where I consider the probability of some subset as being proportional to the non-negative coefficient. If I just scaled so that all these non-negative numbers sum to 1, then I would get a discrete probability distribution. In some sense, this is just bookkeeping, right? I have finitely many non-negative numbers. If I scale them globally so they sum to 1, I get a discrete probability distribution. And I'm just going to record them with a polynomial. One of the benefits of doing this is that common operations on polynomials correspond very nicely to common operations on discrete probability distributions. If you think about what happens when you take a derivative, what terms survive when you take a derivative, and maybe you have to bump up the degree again, the terms that survive are exactly the terms that had the variable xi in them. And so you're only keeping subsets that contained the element I. Similarly, if I set a variable equal to 0, then the only terms that survive in this polynomial are ones that didn't have that variable in them. So it's a useful bookkeeping. And even more useful is that sometimes you can functional properties of f as a polynomial or as a function on r to the n can translate into useful properties of this discrete probability distribution. High level, so not only is sort of recording things as a polynomial convenient, it's very convenient. You can really translate properties of f as a function into properties of this probability distribution in a useful way. And the functional property of f of the day is going to be log concavity as a function. So that's the connection with log concavity. So if I have some polynomial with non-negative coefficients, I'm going to say it's log concave on the positive orthant if either it's identically 0 or it's non-zero, in which case it is positive as a function on the positive orthant, meaning that if I compose with log, I get a well-defined function. And I want the function log of f to be concave on the positive orthant. Really, its Hessian is negative semi-definite at every point in the positive orthant. So it looks a little weird. We're going to go through this in more detail in a bit. And not only do I want f to be log concave, but I also am going to require all of its derivatives to be log concave. So I'm going to say that f is strongly log concave if whenever I take any derivatives of f, however many times, let's see, where did, so here, partial I is really taking a derivative with respect to the variable x sub y. And no matter how I take derivatives with respect to various variables, however many times, I always end up with a polynomial with this property. Okay. just to do an example, so the simplest way to get an example of such a polynomial is to take a real-rooted univariate polynomial whose roots are non-positive. So for example, here's a nice univariate polynomial with roots minus Ri. And I claim that this is log-concave on the positive real line. And I do this by the busting out my calculus and taking the log and taking two derivatives of it. And what happens is I get a nice rational function whose poles are all negative. And so I get that the second derivative of the log is non-negative as a function on the positive. Is non-positive as a function on the positive real line, the way we want it. Right? And so this means this function is log-concave on the positive real line. And in fact, I claim that its derivatives will also have this same property, because if I take a real-rooted polynomial and I take a derivative of it, all of its roots will again be real and be forced to interlace. Here's a picture of f in blue and f prime in red. And so again, for the derivative, I can write it in this fashion for different roots, for now red roots rather than blue roots. And I can do the exact same computation, and I again see that the log of f has to be concave as a function on the positive real line. So if you keep going, this will be true for all the derivatives of f, and so it has to be strongly log-concave. I should just mention that so in a recent paper by Peter Brenden and June He, it was shown that there's various ways of writing down this, equivalent ways of writing down this condition of being strongly log-concave. And for homogeneous polynomials, it's the same as a condition called Lorentzian, which they study and also find to be useful. Okay. So far, we only have one example, and it's univariate, which is not super exciting. But a multivariate version of real rootedness actually comes from real stable polynomials. So if I have some polynomial with non-negative coefficients, I'm going to say it's stable. If whenever I restrict to a line in a positive direction through any point w, I'm going to get a univariate polynomial, and I want that univariate polynomial to be real rooted. So you imagine in this picture, if I restrict to any line in the direction of pointing in the direction of the non-negative orthant, then I've drawn the zero set of a stable polynomial. I'm going to find 4 points, 4 real roots, regardless of how I wiggle my line around. And one of the nicest ways to get such a thing is actually by taking the determinant of a linear matrix whose coefficients are all positive semi-definite matrices. Another way to get such a thing is to start with a stable polynomial and take a directional derivative of it in a non-negative direction. So for example, you can check that just the product of all the variables satisfies this condition, is stable. And if you take a derivative of it with respect to the all ones vector, just sum up the derivatives with respect to each variable, you end up, so this shows that this nice little quadratic is also stable. And in fact, so if your polynomial is stable, then it is log-concave on the positive orthant, sort of a much harder version of this calculus exercise that we did on the slide before. And also, if you take a stable polynomial and take a derivative of it with respect to a variable, you again get a stable polynomial, which is again log-concave on the positive orthant. So again, if you keep going, keep taking derivatives, you keep getting stable polynomials with non-negative coefficients. then they continue to be log-concave on the positive orthant. So polynomials you get this way are also strongly log-concave. Even just this example of taking polynomials coming from determinants, you can get a lot of nice polynomials just by restricting to this case. Even restricting to the case where these matrices have rank 1. So I just wanted to throw a few examples at you. So if all of the matrices have rank 1, really a vector times its transpose, then exactly you get one of these. The determinant is going to be one of these polynomials where no variable shows up with degree more than 1. And the coefficient of corresponding to any subset is actually going to be exactly the determinant. So if these are vectors and say r to the d, then you'll get a degree d polynomial. And if you take any subset of d of them, you can form them into a little d by d matrix, take its determinant and square it, and that will be the coefficient that shows up in this polynomial. So for example, if we pick 3 vectors in R2, 1, 0, 0, 1, and 1, 1, then we get a little 2 by 2 matrix, and we take its determinant, and we again get this quadratic elementary symmetric polynomial. We again see that it's stable. A bigger example is that actually if you want polynomials indexed by the spanning trees of any graph, it can be written as the determinant, basically by the matrix tree theorem, or a weighted version of the matrix tree theorem. Is that if you're interested in the spanning trees of a graph, you can write them down as a polynomial by associating a square-free monomial to every spanning tree. And this polynomial can also be written as the determinant of a linear matrix, where the coefficient matrix of every variable is a positive semi-definite matrix of rank 1. So it's basically, so for every edge has 2 vertices, and you, so the rank 1, let's say, if you have an edge ij, then the rank 1 matrix is going to come from ei minus ej, but you have to basically chop off the one of the coordinate vectors to make them linearly independent. And so both of these examples are really the basis generating polynomials of matroids. So this is the uniform matroid of rank 2 on 3 elements. This is the graphic matroid corresponding to this graph. And in this case, both of these polynomials are stable. For other matroids, this no longer is the case. And actually, the question of what matroids show up as the support of a stable polynomial is a really complicated one. But one thing that we'll see is that actually if we expand from stable polynomials to log-concave polynomials, this connection becomes very tight. So just as a quick primer to the theorem I'll show you, so I'll just remark that so if I have a polynomial, it has non-negative coefficients, it's log-concave at a point in the positive orthant if its Hessian is negative semi-definite. And if we actually write out its Hessian, what we get is f times the Hessian of f minus the gradient times its transpose over f squared. And we're going to evaluate that all at our favorite point. So the f's are just constants. What we get is we get a constant times the Hessian minus a rank 1 matrix is negative semi-definite. And what this is going to mean is that the Hessian evaluated at this point has to have at most one positive eigenvalue. You can convince yourself, you take a matrix, you subtract off a rank 1 matrix, and you get something negative semi-definite, then you must have started, your original matrix must have had at most one positive eigenvalue. So just for example, if we take this polynomial, which hopefully now we believe to be log-concave, and we take its Hessian. It's a quadratic, so we don't need to evaluate anywhere. This is the all ones matrix, which is rank 1 minus the identity matrix. It has one positive eigenvalue and two negative eigenvalues. So something we were able to show is that there's a very tight connection between strong log concavity and matroidness. In particular, if you have a homogeneous polynomial that's strongly log concave, then the set of subsets that show up with non-zero coefficient actually must be the bases of a matroid. Moreover, you start with any matroid. You can take all the coefficients to be 1, and the resulting polynomial that you get, sum over all of the bases times the corresponding monomial. That polynomial is strongly log concave, satisfies this property. So we already did this example. This is the basis generating polynomial for the matroid with bases 1, 2, 1, 3, and 2, 3. It's log concave. You can check that if I have the subsets 1, 2, and 3, 4, they're not the bases of a matroid. If I take the Hessian of this little polynomial, I get something with 2 positive eigenvalues. So if I take a non-matroid, I get a non-log concave thing. Okay. Any questions so far? Yeah.
I have two actually. So do we have I know you mentioned that it was hard to actually go the other way around if I have the basis of matroid with polynomial I'm actually getting in the end. One of the questions is, can we find a non-example of the form, here's a basis of a matroid and here's a polynomial that's not strongly log concave?
If you're willing to really mess with the coefficients, then yeah. You can imagine you can basically, I could have a polynomial of full support, but I can sort of let all coefficients except these tend towards 0. And the set of strongly log concave polynomials is closed. So at some point I have to leave. If this is the limit point, then I'm going to have to leave. Yeah.
And so the second question is, so I think you remember that those strongly log concave polynomials, this support is actually one of those discretely convex sets. Is that correct?
Yeah. So this is. There's a more general statement which I didn't put up, which is that in general you get all the integer points in an M convex set. That's the support of a strongly log concave polynomial. And in fact, there's a lot of names for them. M convex or a generalized permutahedron. Polytopes where all of the edges are parallel to EI minus EJ. Like differences of just 2 coordinate vectors. Those are the polytopes that show up as support.
And is it hard to go from this to the basis of a matroid?
There's actually a nice characterization of being the basis of a matroid is that you're a 0, 1 polytope where all the coordinate sums are fixed with exactly this property, that all of the edges are parallel to EI minus EJ. That's actually a characterization of matroids. Yeah. But I decided to just stick with the matroid. So there's a generalization of this for. So here everything is sort of subsets of n, which corresponds to like 0, 1 vectors. There's extensions to this to like other collections of lattice points, but I decided to not talk about that for the day. Okay. So we have some this is at least one example of a polynomial, of an interesting polynomial with this property. And what as promised in the beginning, what I want to do is think of this as corresponding to a probability distribution on the bases of a matroid. So this, having all coefficients 1 mean I'm taking the uniform distribution on the bases of a matroid. And what I do is use this somehow. I'm going to use it as follows. So we're actually going to define a random walk. And it's a little involved, so bear with me. But so if I have some simplicial complex, which you should think of as a collection of subsets of 1 through n that is closed under inclusion, and I want to assume that it's pure dimensional, meaning that all of the maximal subsets have the same size. So in particular, the independent sets of a matroid form a simplicial complex. And that's going to be the big example of the day. But if I have such a thing, I'm going to define some random walks. First, let me pick out the collection of subsets of some given size, so size k. And let me weight the top dimensional faces, so the maximal subsets in my set. I can assign them some positive weights. Maybe I assign them all weight 1. That's fine. And what I can do is I can record all of this data, as I like to do, in a polynomial. And so for me, I'm just going to record this in a polynomial where I sum over all the maximal subsets, take the weight, and then I multiply it by the corresponding binomial. OK. And we'll just hold on to that for a moment. What I'm going to do is I want to concoct the following random walk. So what I'm going to do is I'm going to define a random walk on the subsets between the subsets of size r, the biggest ones, and the subsets of size r minus 1. And what I do is I start with some subset, and then uniformly at random, I'm going to pick an element and toss it away. And I'll have a subset of size r minus 1. OK. And then I'm going to add an element back in to bump myself up. And I'm going to add in an element j proportional, with probability proportional to the corresponding weight, to the corresponding coefficient. So all the different ways that I could add something back into my set, including adding I back in, that's fine. I'm going to do this with probability corresponding to the weight. OK. And this will define, and I could do a couple things. I could, so in particular, if I do this twice, what I'm going to get is I'm going to get a random walk on subsets of size r. What I'm going to do is study this random walk on subsets of size r. In particular, I could do two things. I could define a random walk on subsets of size r, where I'll call the down-up walk, where I first throw an element out and I add one back in. I'm going to denote the quite large, or potentially quite large, transition matrix for this by a p with a down and up on it. I could do the reverse, where I could start with a subset of size r minus 1. I could add an element to it using these probabilities, and then I could delete an element uniformly at random. And this will give me a random walk on the subsets of size r minus 1, which I'll call the up-down walk, right? Add an element, throw an element away. And this has some potentially very large transition matrix, which I'll denote this way, up, down. And in fact, to analyze what happens with these, it's actually useful to do something even more complicated, which is to make even more random walks on subsets of these. So in particular, if I take a derivative with respect to the all ones vector, I get a polynomial of degree 1 less. And I could play the same game with this polynomial. Right? Its coefficients will give me transition probabilities. And this will define up, down, and down, up walks between the subsets of size r minus 1 and r minus 2. Where I take a subset of r minus 1 and I throw an element away with probability 1 over r minus 1. And if I'm sitting at a subset of r minus 2, I add an element back in with probability proportional to the coefficient in this polynomial. And I could keep going. If I kept taking derivatives, I keep dropping down the degree. It's not clear this is useful, but I could do it, right? I keep dropping down the degree. And this will, these coefficients will give me an analogous walk between subsets of size r minus 2 and size r minus 3. And I'm going to keep track of all the probability trends. I could write down all these probabilities, transition probabilities, down, up, up, down. I could keep going. We go nuts, right? We keep going. And what actually happens is that in order to analyze these random walks on really large, the n choose r-ish subsets, it's useful to analyze potentially much smaller random walks. Okay, this is maybe the most technical part. But so we're going to call this collection of a simplicial complex and the corresponding weights an alpha local spectral expander if it satisfies two things. One, and basically both of them are going to be some condition on sort of much smaller parts of this large collection of random walks. So criterion 1 is that whenever you take a subset of your simplicial complex of size k, and you take the derivative, the corresponding derivatives of f, which basically kills, which basically contracts by this subset S, and you take enough derivatives with respect to the all ones vector to get it down to a quadratic polynomial, that the corresponding up-down walk you get from this is connected. You need a sort of connected graph on your elements. Let's not worry too much about it. Some combinatorial condition on your simplicial complex. And then the second criterion is that for every subset of size d minus 2, when you take the corresponding derivative of your polynomial, again you get a quadratic. The up-down walk given by this corresponding to this quadratic, you have a bound on the second eigenvalue of the transition matrix. And there's an alpha here, and there's an alpha there. You have some bound on the second eigenvalue of this transition matrix. So this is some combinatorial condition on the simplicial complex, and some continuous condition depending on the transition, depending on these weights. And let's not worry about the details too much. But the way it plays into this story is there's this rather remarkable theorem that you can actually use this information, combinatorial information, and then a bound on eigenvalues of much smaller matrices to give a useful bound on the transition matrix of one of the giant matrices. So in particular, if the simplicial complex and the weights are a zero local spectral expander, then the second eigenvalue of this giant transition matrix you get for the down-up walk on the top dimensional faces has the second eigenvalue is bounded away from 1. And the reason why there's a very nice thing that happens, which is this actually exactly corresponds to the polynomial that I wrote down being strongly log-concave. So this collection, the simplicial complex and the coefficients, is a zero local spectral expander if and only if the corresponding polynomial, whose coefficients come from these weights, is strongly log-concave. And just as I'm not going to prove this, but just as a hint of why this is true, so this matrix in play here, coming from the derivative, you can actually write in terms of the Hessian of this polynomial. And way back when, we said that if you have a strongly log-concave polynomial, then you know something about the second eigenvalue of the Hessian of this has to be non-positive. And that actually will translate directly into this condition. So in particular, if you actually go through and write out the transition probabilities, you work your way all the way down and write out the transition probabilities, what you get is you get the Hessian of this polynomial, which is log-concave, times a diagonal matrix to make it into a transition matrix, and then you lazify you make the random walk lazy. And so in particular, you have this condition with alpha equals 0 if and only if this, there's an f missing, if and only if the Hessian of this polynomial has second eigenvalue at most 0.
So some parts of this seem a bit mysterious to me. I'm curious if you can clarify some of them. So I know for high-dimensional expanders, there are like many different conditions people have studied in the literature.
Yeah.
So people studied this notion of local spectral expander without knowing this log-concavity of polynomials, because it seems like, in order to define it, you're talking about taking partial derivatives over. So like,
yeah.
Did this exist without?
This did, and I have not written it down the way it's written down in this paper. Because
could you tell a bit more about how it's written down in the paper?
Well, they basically.
Is this related to like co-systolic expansion, or is it?
I have no idea. No, so they write down. So what they do, they start the same way. They start the same way with simplicial complex and putting weights on it, and then you can define weights on all of the faces of lower dimension by having them be the sum of the weights of the things directly above them.
And then that mimics this partial.
Yeah. So basically I was just trying to write it down quickly and using polynomials. But yeah, you can write down the same thing without the polynomials in them. And that's basically what they do. In this case, polynomials turn out to be sort of a nice way to keep track of a lot of this information. Yeah. Yeah, but the original, yeah. You can do it without touch. If you hate polynomials, you can do it all without touching any polynomials. Until 11:45?
Yes.
But yeah, I like polynomials, so I write down everything in terms of polynomials. And so in particular, there are some corollaries of this. So the basis generating polynomial of a matroid is strongly log-concave, and so you can do this for the independence complex of a matroid. And in fact, if you do a little more work, you can show that you can use this to show that the basis exchange graph of a matroid has expansion at least 1. And in particular, if you want to do this top dimensional walk, so you take the independence complex of a matroid, and you walk around on the top dimensional faces, you're walking around on the bases of a matroid. And the down-up walk that I defined for the bases of a matroid has mixing time on the order of the rank squared times log of n. I should say Nima is going to talk about, I think, an improvement of this maybe in the next talk. But this is sort of comes out of this story. And just as a, it's not clear that this will help, but so just as a quick example. So if we took the spanning trees of this graph, then I could write down has 8 spanning trees, hopefully all of which are represented here. And I could write down the basis generating polynomial of this thing. And I could write down this simplicial complex whose maximal faces corresponding to spanning trees. And then I could look at all of the things, all of the subsets of this. Right? I can make this graph where I put an edge if one set is contained in the other, directly contained, with a difference of just one element. What I can do is I imagine walking around this graph. And one thing I can do, one thing I could do if I take the derivative with respect to the all ones vector, I get some quadratic polynomial. And this will give me weights on all of these subsets of size 2, and I can use them to define I can use them to define a random walk between things of size 1 and size 2. And in particular, one of the conditions, the combinatorial conditions that I wrote down before, is that if I think of this as a graph on just 1 through 5, where I connect 2 things if I can get between them by going up and then going down, this graph is connected. That was one of the combinatorial conditions. And then the other condition was that if I take derivatives to get down to a quadratic polynomial, so if I take the derivative with respect to x1, for example, then I get some polynomial. And in fact, it looks exactly like the link of the simplicial complex over the element 1. And this will define me some random walk, some pair of random walks on this subgraph. And the condition, one of the conditions was on the second eigenvalue of the random walk, the up-down walk I get from this derivative. And somehow putting together, information about this tiny random walk, and let's call this tiny random walk, can tell me something about the random walk between the top level and the second level. Okay, so just to sum up, so strong log concavity turns out to be a useful, and I guess I didn't say it, but testable condition on polynomials. Many interesting polynomials have this property, in particular the basis generating polynomial of a matroid. And if you have such a polynomial, then it gives you guarantees for some random walks mixing quickly, and in particular, this gives you sort of these local spectral expanders. This is the sort of corresponding matroid polytope for the spanning trees of this graph, and the 0 set of the corresponding stable polynomial if you're curious. And with that, I will thank you for your time.